All right, in this next few lessons, we're going to talk about related rates. And related rates is kind of like the meat and potatoes of derivatives. It's where everything comes together, and this is what a derivative does, okay? And this is the basis to larger problems that you're going to work in higher order math, okay? We're talking like big math, big boy math, and big girl math, and big architecture things or big engineering things. These are the baby word problems that lead to all of that. All right. And the best way to kind of go through these word problems is a couple steps. One, as you work through an example of a word problem, work through that word problem several times until you can get the right answer every time, and that you can set the problem up on your own every time. Sometimes setting the problem up on your own is the most difficult part. So um, work this first example through a couple times. Do you see where everything's coming from? Do you get it? Do you not? Are you sure? Are you unsure? There's some great internet resources. Just type in calculus related rates into either YouTube or Google, and you'll get a lot of different things. Because sometimes on this, you need to hear more than one person speak. Also, with related rates, there's like a little process you're going to have to go through on each one. Each problem is unique. I can't go, okay, on this problem we're going to do this, and then this, and then this. All these problems are just a little bit different, and that's what kind of makes them fun. They're like a little bit like puzzle pieces. You have to figure out what puzzle pieces you need and put them together in the right way to get a cool shape and fun puzzle. All right. The problem is it's a trick puzzle kit, and they give us a few extra pieces, so we have to figure out what to not use. All right. Um, for those of you in my class, your book gives you a strategy for solving related rates. You need to understand what the problem is. What are they asking you to find? Is it the area of a circle or a sphere or a cylinder? Is it the perimeter of a rectangle? Are they asking you to find distance? What are they asking you to find? Then figure out a mathematical model to relate all those things together. Again, it could be setting the area equal to a specific number that's listed in the problem, or who knows what. You're going to write out your equation that relates all of these different things together, and sometimes that might be two equations. You're going to write all those things out and find out what their relationship is. You're going to take the derivative of both sides of your equation. You're going to substitute any values that you were given as a starter value, like you started here, you stopped there. And then you're going to interpret what your solution is. And that's really a critical part. Let's say, for example, we're talking about cars that are chasing each other, and you get some sort of how fast is car B going, and you get 3,462 miles an hour. Guess what? You've probably got an error in your math. But if you do that same problem and you get something where car B is going 83.6 miles per hour, well, now you're onto something. So it's really important to kind of understand initially what that whole problem's asking you for. So this first guy is, a little softball to lob at you to see if you can get everything figured out and see what we're going to do. But critical thing here, create a problem, create a model, determine your equation, and differentiate or take derivative of both sides. Okay, so let's just start with what we've got. The radius of a sphere is a differentiable function of t, and allow v to be the volume of the sphere. Find an equation that relates change in volume with change in radius. And what does that mean? Change in volume would be something like the change in volume over the time. Okay. What about the change in radius? That would be something like dr dt, the change in radius over the change in time. These are the things that we're going to be interested in. So let's talk about this. We've got a sphere with a volume. So we know we're going to have some sort of volume situation developing here. So the volume. Now you may need to Google this, so if you need to, just pause and go do that. But what is the volume of a sphere? Like, what's the equation? And the equation is 4/3 pi r cubed. That's it. Now, how can I get dv and dt out? dv, dt, and dr dt? Well, remember, we're talking about a function over time, okay, f of t. And we're given this equation. We've got our equation here of volume and radius. Those are the only two variables. 4/3 pi is a constant. So what I can do is take the derivative of both sides. Now, when we do this, we would have v prime equals 3 times 4/3 pi r squared. That's your derivative, okay? Clean this guy up. You'll notice that the 3's divide out, and I'm left with v prime equals 4 pi r squared. Now, remember, since t was our original variable here, the thing, a differentiable function of t, we need to add behind the r a dr dt. Okay, it's pretty important to add that part. So we would just carry him down here, dr dt. Now, the cool thing is we're actually done with our problem at this point. Okay, we've taken a derivative of both sides. The weird thing is the left-hand side looks like v prime. The right-hand side has that dr dt in it. That's the relationship we're looking for. So what do? Well, we just keep in mind that v prime has a whole slew of different ways that it could look. V prime is the same thing as dv dt, which is the same thing as d. Let's see here. That's not it. V over dt. Or v prime of t. Like, all these different things are the same. And the one that we want is right here that compares volume and time. So we would just finish our problem off by saying dv dt is equal to 4 pi r squared dr dt, and that is the end of our problem on this particular case. That's all we needed to do. Find an equation that relates change in volume with change in radius.